Okay, in this video, I'm going to be talking about lipids. It's the second macromolecule that I'm discussing in this chapter. Lipids, for the most part, the biggest thing that we need to focus on is what is their properties and what do we really need to fixate on in terms of their use. One of the biggest parts about lipids is that they're hydrophobic. That means they do not like to mix with water at all. And they are often referred to as being nonpolar. So you want to think of those two as almost synonyms of one another. Hydrophobic versus nonpolar, they're going to be essentially the same thing. And you're typically going to see them in fats, steroids, and phospholipids. This is just kind of showing you it's not something required, but it's an interesting overview of what do lipids do. If you take in fats, what do you do with them? Well, you have some lipids in the blood. You can store that as fat tissue. Oftentimes it can be used to actually be broken down. And we can use it for cellular respiration as well. So a lot of different uses for lipids, but the biggest and most common thing about lipids is really a triglyceride, which is going to look something like this. So this thing right here is a fatty acid. So this is not what we're going to call a complete fat molecule or the fat that we're used to seeing. But the biggest component about this is that anytime you see one of these long branches of carbon and hydrogen, this is what we're going to be calling a hydrocarbon. So this is one fatty acid. It's going to be linked with a glycerol molecule. The common theme for this unit is anytime you lose that hydrogen and those two hydroxides, that's a dehydration reaction. So to make a complete fat molecule, a triacylglyceride, the fats that you're known and used to, it would be looking something like this, to where you actually have those three fatty acids, and that's going to be the fat that essentially that you would eat, a triacylglyceride. So when you think about sorry about this, one additional component, this is kind of showing you the overview of how these are formed. In terms of saturation versus unsaturated fatty acids, really the big component about saturated versus oh, here's the video. So this just shows you that how these fatty acids are attached. It's the same thing as a dehydration reaction. So all of these are your nonpolar hydrocarbon tails, all held together by a covalent bond here. So in terms of what your big concern is going to be with for this, this is just showing you that these fatty acids can vary in length. There's no one set ratio of how long that tail has to be. This is showing you that if you get a double bond like this, it means you've actually lost one of those hydrogens, and that causes this kink in the tail right along here. So I would say that these two on the bottom are going to be saturated fats, and this would be an unsaturated fat. So when you think of saturated fats, they're going to be solid at room temperature. Most of your fatty tissue is saturated. Unsaturated fats are going to be things like your cell membrane is going to be made up of unsaturated fats, but also they're going to be typically a liquid at room temperature. So this just kind of shows you that the caloric intake, not something you guys have to know in terms of the energy use, but one of the bigger functions of these lipids, not only do we get a lot of energy with them, we can actually store energy, not as glycogen, but we actually store it as fat. It helps insulate for temperature changes as well. But the biggest thing that I'm going to almost guarantee that if you do get a question on this, it'll be on phospholipids. Now, the reason we throw this in is because here's showing you a lipid component. This one on top, I would say, is a saturated lipid because it's that straight, it has that straight rigid structure. This one right here, I get this kink that I already have highlighted from when we talked about in class. This little kink is showing you that it is unsaturated. So it causes one double bond here, and that makes it have some type of flexibility to it. So this, as we talked about in the previous videos, this would be your polar head. So you got your phosphate group here. So this would typically be a really polar or negative charge. And all this right here would be nonpolar. So this is a more realistic, or I should say appropriately drawn version of a phospholipid. Here's your your hydrophobic tails. So here, each one of these is representing carbon, hydrogen, carbon, hydrogen. You get your double bond here, and then there's your phosphate group there. So all three of these are just showing you different representations of the same thing. So in terms of these phospholipids, this is just showing you have the non-polar region on the interior of the cell membrane, and then the polar heads. And the last type of lipid that we do need to at least mention at this point is steroids. Steroids are going to be embedded within the membrane, but they're also going to be acting as a cell signal. So in the previous video, we mentioned that they can actually pass through the cell membrane directly because they are nonpolar. So as they diffuse right through, they can sneak through that membrane because they are nonpolar. All right. And that's it for fats.